Though this question was worth 12 marks, many students struggled to get past the first couple of marks. The examiners note that this was a challenging question, which candidates struggled with after Part A. That's after the first 2 marks. Many candidates did not even reach Part C. Part A. Express this in partial fractions. We have our partial fractions here, where we have A and B. We multiply both sides by the denominator here to cancel out all of the fractions. We'll end up with this. Next, we can set V equal to 0. That will cancel out this term here. Substituting in V equals 0, we end up with this, which leads to this, and therefore A is 1/25. Next, we can ensure that this bracket is equal to 0 by setting V equal to 25. Therefore we get this, which gives us this, and therefore B is this value. If we substitute our values of A and B back into the original equation here, we end up with this. And then we can factor out the 1/25 outside the bracket here to leave us with 1 on the top of each fraction. What next? It says the volume V in microliters of a plant cell T hours after the plant is watered is modelled by this differential equation. The plant cell has an initial volume of 20 microliters. Find, according to the model, the time taken in minutes, not hours, for the volume of the plant to reach 24 microliters. So let's start with the differential equation that they gave us. Now notice that we need to separate the variables here. We need to bring all of the V terms onto the left-hand side to be with the dV, and bring all of the T terms, if there are any, onto the right-hand side. But we can only do that by multiplying and dividing. So I'm going to divide both sides by what we've got here, imagining that there's a 1 here. I'm also going to imagine that I'm multiplying by dt. That will bring the dt to the other side. That leads to this equation here. So we've got all of the V terms here and everything else on the other side. From part A, we can rewrite this part in partial fractions to help us to integrate this. So let's substitute this in here. I'm just going to leave the 1/25 on the outside of the integral. I'm allowed to do that because there's no V term there. It's just a multiplicative constant. You can leave it on the inside if you like. I just think it looks neater on the outside. Next, we can integrate. This gives us natural log of V. And be careful about the next term because we've got a minus V here. Remember, we're going to need an extra minus sign on the outside when we integrate. When we integrate this constant, well, we just get 1/10 t, and don't forget the constant of integration, the plus c. If you get that far, you get your first couple of marks. Next, we can note that it said that the initial volume was 20. So when it says the initial volume, it's talking about the volume when time equals 0, at the very beginning, initially. So we can substitute those two values in. When v equals 20, t is going to be 0, so we replace the variables with their numbers, like so. If you do the number crunching, we end up with this. And then we can use a rule of logs that says that when we subtract logs, we divide the arguments. So we divide 20 by 5, and that gives us natural log 4. So that's our c value. We can then replace that c value back into this equation where it first appeared. And there it goes. What's the question asking us to do? It's asking us to work out the time in minutes when the volume is 24. So when v equals 24 microliters, notice that matches the units up here, and we'll end up with this. If you do the number crunching here, we end up with the natural log of 1, which you should know is 0. We can also subtract this natural log from both sides to isolate our 1/10 t. Next, we can factorise this term and this term, noticing they've got 1/25 in common. Then we can use that rule of logs again. When we subtract two logs, remember that we divide their arguments. 24 divided by 4 gives us 6 here. But remember, this answer is in hours, as it says in the question here. And we need an answer not in hours, but in minutes. So we need to convert that hours into minutes by multiplying our answer here by 60. And if you do that, that gives you about 43 minutes. Make sure you do that to get the very final mark. Part C, we're asked to show where this formula comes from, where we're trying to find out what these constants A, K, and B are. So from part B, remember we had an equation, the one we've got here. We need to make V the subject. So I'm going to first get rid of this fraction by multiplying both sides by 25. So I'm multiplying all of this by 25, multiply this term by 25, we'll get a 25 on the top. And this term here, well, this will just give us 1 here, so just natural log 4. Next, again, we use that rule that when we subtract two natural logs, we divide their arguments as follows. Next, we want to get rid of this natural log. What's the opposite of a natural log? Well, the inverse is taking an exponential with base e here. So we've got e to the power of the left-hand side is the same as e to the power of the right-hand side. Why do we do that? Well, when we take an exponential of a natural log, those two things cancel one another out. It's like multiplying by 3 and dividing by 3, or adding 2 and subtracting 2. It has no effect, so we're left with this part on the left-hand side. What can I do with the right-hand side? Well, I can split this up using our rules of indices. I know that when you multiply two things of the same base, you add the powers. So I'm just applying that rule in reverse here. I'm turning this plus sign into two separate exponentials with the same base, e, except we're now multiplying them. Why would I do that? Well, we can tidy this up. Again, exponential and natural log are opposites. They will cancel each other out, leaving us with 4 here. Remember, we're trying to make v the subject, so we want to get rid of this fraction. How can we do that? Well, start by multiplying both sides by the denominator. So I'm multiplying this by 25, that will give me this, and this by minus v, that will give me this. Next, we bring all of the v terms onto one side. How do I do that? Just by adding this term to get this. Then we can note that this term and this term have a v in common, so we can factor that outside of the brackets. Next, we can divide both sides by this bracket, so it ends up on the bottom. But this doesn't yet look like what we've got here. I need just a constant on the top of the fraction here. So really I need to get rid of this e to the power of 5 over 2t. How can I do that? Well, I can multiply top and bottom of the fraction by e to the power of negative 5 over 2t. Because when I add the powers here, because I'm multiplying, the power will give me 0, and e to the power of 0 is just 1. So that would just leave me with 100 times 1, which is just 100. When I expand the brackets on the bottom, I end up with this. So there we are, we've got the answer in the right form. Part D. The model predicts that there's an upper limit, which they're calling L, microliters, on the volume of the plant cell. Find the value of L, giving a reason for your answer. So from part C, we had this equation here. What would happen if t became really large? In fact, what would happen if t went towards infinity? What's going to happen to this exponential function here? Well, because it's got a negative coefficient, think of the graph. It's going to tend towards 0. So that means as t goes towards infinity, v is going to go towards 100 over 0 plus 4, which is 25. So that's a way of getting our upper limit, what they're calling L, for our final mark.